Hello everyone, hello students. We are going to start with BVLSI lecture number 45 today. So let me start. Lecture number 45, and today's date is 14th April. Alright, so I think we will continue slightly a discussion on CMOS inverters, and then we'll summarize all the formulas required for solving the numericals. So CMOS inverter, we were discussing a CMOS inverter topic. It consists of a PMOS pull up and an NMOS pull down transistors. Input is applied to the gate terminal of both NMOS and PMOS. Output is taken from the drain terminals. Okay, so this is my PMOS load and NMOS driver. Alright, and let's summarize the VTC curve. That's what we have been doing so far. So this is V out versus V in curve. It has 5 regions of operation. Okay, so among these 5 regions of operation, let me mark few of them. So here we have region A, then here we have region E, alright. At the center, this is VTH curve, the switching threshold. This is VTH, this is VTON, okay, this is VDD plus VTOP, this is VDD. Okay, so we have discussed yesterday quite length and breadth. This is region number A, this is E. Region C is quite small, quite narrow, but yeah, this is region C. Similarly, here we have D. So this is region C, B, and here it is D. Alright, so we have seen that in region A and E, at least in region number A, your NMOS is off, completely off. So if you see the current in this region, it should be 0. So here the current in the circuit is 0. Okay, because one of the transistor is off. Similarly, in region number E, PMOS is off. Okay, because V in is greater than VDD plus VTOP, and here also if you see the overall current ID, it's 0. So region number A and E does not dissipate or does not contribute to any current. Alright, and yesterday we have seen one, let me show it to you, one graph. Yeah, this one, I think it was in lecture number 44A. Yeah, so if you see these characteristics where we have overlapped the currents and the voltages, the VDS voltage and ID current, right? In can you see identify these points where I have denoted by this pink color dot, then brown color I have written there D, E, C, B, A. So if you see carefully in A and E, the current is 0. Okay, B and D, there is slight amount of current flowing. And where do you get the maximum current from? Maximum current you get at C. So correct, agree? So at region number C, both the transistors are in saturation, and that's why we get a maximum current, whereas in B and D there is slightly less current. Okay, so if I want to draw the current graph for this curve, there is one more line which I forgot to draw on. This is V out equal to V in line corresponding to VTH curve. Okay, what is this point called as? VIL. This point is called as VIH. Or if you take it that way. Okay, let me just, yeah. So right now what I am doing is I am drawing the current graph, current flowing through the circuit. So let me draw it a little bit bold. Now the current flowing in region number B, as we have seen, it's slightly there. So here it is 0. In region number E it is 0, and it is maximum in region number C. So you can draw it. Okay, if I'm not wrong, yeah, this is the current. So this graph is of the current. Okay, ID, and we know that IDP mod is equal to IDN. Current flowing through NMOS and PMOS should be almost same in magnitude. Okay. Alright, so here as you can clearly see, the current in region number C is the highest, and it's declining down as we go on to region number D, B, and then A, it is 0, current is 0. So how can we summarize this? We can summarize it as follows. So please write down. First point is, okay, yeah. So the first point is ID current flowing is 0 for V in less than VTON, or we are in region number A. Okay. Second, again the ID current is 0, the drain current is 0 whenever V in is greater than VDD plus VTOP. That is region number E. And third case, the current ID is maximum. ID is ID max when V in is equal to VTH, that is equal to V out. So write the summary, or we call it in region number C. So region number C, when both the transistors NMOS and PMOS are in saturation, and it makes sense, if both are in saturation, the maximum current flows in the device. Alright, so these are the power supply. Okay, these are the power supply currents. Let me reduce it a little. Power supply current versus input voltage for the CMOS inverter. Okay, alright, so please note it down. Let me change the writing pad code, it's giving some trouble. Till then you note down this formulas. Alright, now it's better. I hope you have noted down. Yes? Okay. Next we go for power dissipation. Next topic will be power dissipation in the CMOS inverter. So the average power dissipation in a CMOS inverter is 0. Okay, power dissipation considerations. Alright. Now if you consider the power dissipation in region number A, in region number A what happens is, the PMOS transistor is on. Let me draw it. So both the NMOS and PMOS are representing in terms of RP, RN, the resistance across them. This is VDD. So in region number A, NMOS is off, so it is replaced with the open switch, and this is on. This switch is on. alright, and the current flowing in the circuit here, it's actually IDP will be 0. Yes or no? Because this is open circuit, so no current can flow, and this is my V out. So this is what happens in region number A. What happens in region number E? Same thing, but I mean these are like switches are applied to the input actually. Here, resistance of the PMOS transistor, resistance of the NMOS transistor, and these are the switches. Now, which switch is closed and which is open? PMOS is open and NMOS is closed. These switches are driven by the input, and here is my output. This is RP indicating the resistance for NMOS and PMOS. Alright, so switch RN is, NMOS transistor is on, still the current flowing in IDN, the transistor will be 0 because it's open circuit over here. Okay, so power supply to the ground, the current is 0 in region number A and E. Alright, and so power formula, average power formula will be given by, let me add over here, PDC, or you can write it as P average DC is given by VDD by 2. So we assume that half of the time the input is low and other half of the time the input is high. So it's given by IDC is the current flowing from supply voltage to the ground, from the VDD to the ground, into when Vin is 0, logic 0, plus current when Vin is logic 1. Okay, this we can write it as follows. PDC is power when Vin is 0 plus power when Vin is equal to 1 divided by 2. Okay, someone has joined, let me add them. No. Alright, so let's calculate this. When Vin is equal to VOL, when Vin is equal to VOL, let me write over here, first point, when Vin is equal to VOL, that is very low, input is low, right? What is my current given by? My drain current will be given by 0. Okay, when Vin is equal to VOL, yes or no? And my power when my input is 0, almost 0, because VOL is 0, right, for the inverter, so this will be 0. And for the second case, what happens? When Vin is equal to VOH, that is logic 1, and this is VDD. Again the ID is 0 because this is region number E. So Vin will be again, when Vin is equal to 1, logic 1, that is VDD, the power will be 0. So the average power, if you consider, it will be 0. That will be VDD by 2, 0 plus 0, and the average power dissipation in the CMOS inverter is 0. Okay, so this is for CMOS inverter. The static power dissipation, this is static DC power dissipation in CMOS inverter is 0. This is one of the advantages of CMOS inverter. Alright, understood this? Now we have few formulas to write down. Now we will be preparing ourselves for the solving the numerical. We have quite a few formulas to write it down, jot it down. Is this clear to you? The average power dissipation at any point of time when the input is very low. Here the input is around VOL and here input is around VOH. So it is average power dissipation should be 0. Okay. Of course, the current in region number C is maximum. So temporarily, if both the transistors are on, then the power is there. But on average, it is 0. Now, we'll spend some time on revising the formulas. You remember we have written for a symmetric CMOS inverter a few formulas, right? So first of all, we'll write, few formulas for the CMOS inverter. We have derived it over a period of time. So first formula is of VTH. So what was the formula VTH? We have two formulas actually for VTH. I'm writing one of them, VTON plus square root of 1 by KR VDD plus VTOP divided by 1 plus square root of 1 by KR. This is one of the formula for VTH, so please note it down. Okay, then we have the formula for I think KR. KR was VDD plus VTOP minus VTH divided by VTH minus VTON, the whole square. Okay, this was another one. Then for ideal inverter, please note down the formulas for ideal inverter. What the conditions were? VTH was equal to VDD by 2. Okay, and for a symmetric ideal inverter, for a symmetric CMOS, what was the value of KR which we have found out? We have shown that symmetric CMOS inverter has VTON is equal to minus of VTOP. So what was the formula for KR for symmetric CMOS inverter? Anyone? It was 1. So note down this formula. Alright. And with this, what was the value of W by L of N by W by L of P given by mu P upon mu N? So this was another formula which we have found out. Okay. And also what was for a CMOS inverter? VOH is VDD. Okay. And VOL was 0. And how we have to find out VIH. So this was possible using two formulas and VIL. You remember we have yesterday solved it, derived the expression for VIH and VOL. So basically we have to solve that together. So we'll see now shortly. You have written these formulas? Yes? Alright. Okay. So what happens is, let me go to this. Yeah, this is where we have derived yesterday. See, VOH was VDD, VOL was 0. Then for the derivation for VIL, we have solved two formulas, right? 2.1 and 2.2. Now if you solve for 2.1 and 2.2 together, okay, and we are having a symmetric CMOS inverter. So solving 2.1, I'm not writing it again. So 2.1 and 2.2 again, I'm referring to the previous PDF. Okay, so solving equation 2.1 and 2.2. This is from BVLSI lecture 44B handout. Okay, and also we are assuming a symmetric CMOS inverter. What do you mean by symmetric CMOS inverter? VTON is equal to minus of VTOP. Alright, so here if I solve these two together, 2.1 and 2.2 together, this is 2.2, this is 2.1. Okay, if I solve these together, what I will get is VIL for symmetric CMOS inverter. This is purely for symmetric CMOS inverter. So I'll get the formula, please note it down. The formula for VIL to be used for a symmetric CMOS inverter is 1 by 8 3 VDD plus 2 VTO. Now this can be VTON, this is VTO. Okay, this can be VTO, can be VTON or VTOP. So this is by solving 2.1 and 2.2 from the previous lecture. Okay, similarly your VIH will come out to be 1 by 8 5 VDD minus 2 VTO. So VTO can be VTON equal to minus of VTOP. They are same. Okay, so by solving, so VIH will go to VIH now. So VIH also we have two equations. Equation number 3.1. This was equation number 3.1 and equation number 3.2. Here it is. So if we solve them together, we'll get the value of VIH actually. Here I should have written VIH by solving 3.1 and 3.2. Sorry, 3.2. So if you solve these two together, we'll arrive at this expression. So please put a box around these expressions because they are extremely important. This is for symmetric CMOS inverter. Please note them down. This will be required in solving the numericals. For symmetric CMOS inverter, the threshold voltages are almost same. Okay, and for a symmetric CMOS inverter, your the noise margin levels will be same. So here if you consider, obviously your VOH is VDD, your VOL is 0, and if you calculate, if you add them together, VIL plus VIH, if you add them together, you will get equal to VDD. If you can check it out. Okay, so here if you calculate noise margin high, that will be given by VOH minus VIH, that is VDD minus VIH. So VDD minus VIH, and if you solve this, you will get it as 3 by 8 VDD plus 2 by 8 VTO. Okay, you can solve this further and calculate this, and obviously noise margin low will be VIL minus VOL. That will be this term VIH, but VOL is 0, so it will be VIL only. So these are the formulas for a symmetric CMOS inverter which you see on the screen. These are the noise margin levels. Alright, so with this information, are we ready to solve a numerical for the CMOS circuits? Alright, can we start now for the CMOS inverter? Okay, so yeah, let me open up with a symmetric CMOS inverter design first. Alright, so write down numerical number 1. Okay, so we are starting with numericals on CMOS inverter. So write down the first numerical. For a CMOS inverter, the following parameters are given. Kn is 100 microampere per volt square. Kp is 100 microampere per volt square. Then VTON is equal to mod of VTOP is equal to 1 volt, and VDD is 3.3 volt. We need to find noise margin levels, noise margin of the CMOS inverter, of the given inverter. Okay, and we know that for a symmetric CMOS inverter, what are the conditions to be followed? Can you tell me? So let's start with the solution. First of all, we need to check whether it's a symmetric CMOS inverter or no. So let us start with the check. So from the given data, can we say Kn is equal to Kp? Yes or no? So we can say Kr, which is Kn by Kp, it is 1. So Kr for a symmetric CMOS inverter is 1. And secondly, is VTON equal to mod of VTOP? Yes, it is equal to 1. So since these two conditions are satisfied, therefore it is an symmetric CMOS inverter design. Are you understanding? If these two conditions are satisfied, then only it's a symmetric CMOS inverter. And if it is a symmetric CMOS inverter, then the solving this, it's like 2 minutes time. Okay, so we will be using the formulas which we have derived today. Understanding this? Now let's solve it further. So C point will be VOH for a CMOS inverter will be VDD, which is 3.3 volt. Yes. VOL for a CMOS inverter, VOL is 0 volt. What is the formula for VIH and VIL? We have just now written today. VIL is 1 by 8 3 VDD plus 2 VTO, which is VTO is actually equal to VTON equal to mod of VTOP, which is 1 volt. So let's substitute that value over here. 1 by 8 3 times 3.3 plus 2 into 1. Can you tell me this answer? What value did you get over here? Hello, let me know this value. How much is this? 3 into 3.3 plus 2 the whole divided by 8. What's the answer? Sorry, anyone with the answer? Hello. Where is my calculator? Let me also check it out once. You have to tell me the answer fast, quickly, because we have a lot of cover up to do for the numericals. How much is the answer? Okay, I am getting around 1.4875. Is this the value you get? Please confirm. Yes or no, just. Hello. Please confirm it fast, because numericals I require your assistance in confirming the answers, because you all are solving it. Is it this value you got? Hello. Can someone reply and acknowledge that this is the value? Next is VIH, that is 1 by 8 5 times VDD minus twice VTO, so that will be 1 by 8 5 into 3.3 minus 2 into 1. So calculate this VIH and let me know the answer. 5 into 3.3 minus 2 the whole divided by 8. So I am getting around 1.8125. Is this the answer you are getting? Right? Okay, next is the noise margin levels. Noise margin low will be given by VIL minus VOL, that is 1.8125 minus 0, that is 1.8125. Remember, for a symmetric CMOS inverter, noise margin levels will be almost be equal. So noise margin high will be VOH minus VIH, that will be VDD, minus VIH is 1.4875, that is 3.3 minus 1.4875. So 3.3, let me check. 3.3 minus 1.4875, is it coming same? Yeah, 1.8125. So as you can clearly see, for a symmetric CMOS inverter, the noise margin levels are equal. Is it good for the design of a CMOS inverter? Yes, very good, because that means equal immunity to the noise, and it's treating logic 1 and logic 0 as same levels almost. So if I wish to plot this in a VTC curve, all these points, they can ask you an exam, I mean plot the VTC curve for the given question. So V out, V in, and if I plot almost like ideal one, yeah, this is VDD, this is 3.3, this is VOH, which is again 3.3, VOL is 0 over here, then we have this will be VIL, and over here VIH. So VIH point is how much? This is VIH 1.8125, and this is 1.4875. So these are the four critical parameters which I marked over here: VOH, VOL, VIL, and VIH. And this is VDD. So if they tell you to draw the VTC curve and mark the critical parameters, this is how you do it. Okay? Have you completed this numerical, everyone? Yes or no? Hello? Can someone reply if I am audible? I have not asked you all. Hello, I am audible, right? Huh, so let me know immediately. Are you all getting these values, all of you all? Yes or no? If I'm getting anything different, then let me know. Getting these values? Yes, no? Alright. So, so let me divide it into two parts, the lecture. So let me call this as 45A and record the other half as 45B. Okay. So up till now we have discussed the modified formula for symmetric CMOS, and we have solved one numerical. Now next numerical will continue in the 45B part. Okay, so let me stop the recording now.